Hello, my name is Johannes Lauinger. This talk is about Unsafe Go Code, and it's a joint work with Lars Baumgärtner, Anna-Katharina Wickert and Mira Mezzini. Now, memory safety is a very important aspect for the security of software because many bugs and vulnerabilities are related to it. In fact, Microsoft stated that 70% of their bugs are accounted for by memory safety alone. And to fight this, many languages have adopted countermeasures. This work is about the Go programming language, and it uses automatic memory management and restrictions on the type system to improve the memory safety. However, sometimes developers actually need to have direct access to the memory, and for these situations there is an escape hatch, and in the case of Go, that is something called the Unsafe API. These legitimate use cases include, for example, code optimization, such as when we want to reuse memory without any reallocations. Further, direct hardware access, like when building a device driver. Accessing foreign functions written in C code or other external libraries may also need unsafe. And then lastly, unsafe allows to achieve features that the language does not have, or at least not yet. For example, Go does not have generic support, at least before version 2. But with unsafe it is possible to achieve this generic functionality. The goal of this work was to find out how dangerous using unsafe is and how often that is actually being done. So how common is it used in real-world software. The talk will be structured into 3 main parts. First, we'll cover the basics of the Unsafe API and go through some possible dangers and exploits. Then I'll introduce our novel static analysis tool go-geiger, which can identify unsafe usages in a project and its dependencies. And also I'll present our study on unsafe usage in open source projects. Last, we'll go over Go Safer, a second novel tool that we developed designed to find known dangerous misuses of the Unsafe API. So let's begin with the definition and some possible exploits. In Go, normally we do not get direct access to raw memory. Well, that is the raw memory addresses. At least we cannot convert a memory address to an actual usable pointer. And similarly, we cannot convert incompatible types between each other. However, there is the escape hatch of the Unsafe API, and with it, this is possible. Now, the Unsafe API is a package of the Go standard library, and it contains 4 members. 3 of them are functions, and then there's also the pointer type. And this pointer type, I marked it with an arrow here, is the most important part of the Unsafe API in terms of its capabilities, because it gives us some additional power. It allows casts from and to any pointer type, and that means that actually it allows casts between any types in Go. And also it allows us to cast from and to a special type called uint pointer or uint ptr that can store an address and also participate in calculations. Therefore, this gives us the freedom of pointer arithmetic. Therefore, with unsafe pointer, we achieve the same level of flexibility and power as we would have with raw void pointers in C. Now, in the following, I'll demonstrate possible dangers and some of the exploits. Look at this code example. In the function main, unsafe pointer is used as an intermediary type to cast from pink struct to violet struct. Both struct types have 2 fields. But for field A, the types are different. They are int and int64 respectively. Go decides between types with a fixed length, like int64, which is 8 bytes, and then architecture-dependent types like int. These can have different sizes, alignments, or byte orders on different target architectures. For example, int is 8 bytes on 64-bit architectures, but is only 4 bytes on 32-bit architectures. Now, normally Go code can be compiled for different target architectures without actually changing the code. The compiler is actually taking care of this, and when it compiles for a specific target architecture, it makes sure that the alignments and the sizes of all the types are used properly. However, this actually means that int and int64 need to be incompatible types because, well, when they have different sizes, when we compile for different architectures, they might not be interchangeable. Now, with the Unsafe API, it is actually possible to convert those, and we see this being done here in the main function when we cast the struct types, and therefore indirectly we're also casting from an int64 to an int value. And this is already the first potential danger that comes with using the Unsafe API, because when we decide to compile the program for an architecture where they aren't compatible, using Unsafe will still make the cast. So in that instance, it might actually be that the violate value gives access to invalid memory that is behind the allocation of the original ping struct. And we call that dangling pointer. We're accessing memory that is invalid and could contain any contents, and therefore this could potentially result in a code injection or an information leak. Now, to understand the second exploit shown in this presentation, please note that Go uses automatic memory management with a concurrent mark and sweep garbage collector. Now, this means that when the garbage collector runs, it determines live values on the heap by finding out which of these values are reachable from variables in scope. And this can be transitive, because values that are live can have further references to other values that then need to be marked live. Right, in this diagram that is shown here, these live values are highlighted in blue. And then all the values that haven't been marked, they're shown in white here, are freed. And concurrent means that the garbage collector can run at any time during the program execution. That's going to get important, keep that in mind. Right, this code here exists multiple times in real Go applications. It is about incorrect slice casts. Now, what is a slice? Slices are kind of a dynamic array. Internally, they consist of a backing array of some size, which is called the capacity of the slice, and a length that indicates the number of elements that are currently in the slice. Elements can be added, which increases the length, and when the length would get higher than the capacity, then the Go runtime in the background will automatically auto-allocate a newer, bigger backing array and then copy over all the data transparently. So it kind of grows dynamically. And strings are slices of type byte, but they still are a different type. So in this example, the function provides a direct conversion between those two, from a string to a byte slice. And it's doing this without any reallocations. And for doing this, we need the Unsafe API. To get access to the internal representation of both the string and the slice, we're using a special type called string and slice header. And to get those, we need to cast through unsafe pointer, because otherwise the types would be incompatible for the type system. Now, in this special type, the data field contains the address of the backing array, and then cap and len are the capacity and the length of the slice, respectively. And here we create a slice header from scratch, and then using unsafe pointer as an intermediary representation, we cast it into an actual byte slice. Now, this is a dangerous and incorrect pattern, as we will see now. Remember that Go uses this garbage collector. The data field in the slice header is a plain address, and as far as the garbage collector is concerned, it's not a live reference. There is a special case that it's treated as a live reference if it belongs to an actual slice or string. This does not work here because the slice is created from scratch. There's only the header, but there is not yet an actual slice. Here's a diagram that maybe better illustrates this problem. We begin with the string and then obtain the string header to access the internals. Both of those are shown in green here, and this header is located at position 1 in the little memory diagram. Now, the header contains a reference to the backing array, which is shown in red here and located at memory position 2. There is a strong reference to this backing array, so the garbage collector will follow it and mark the memory as live. Now we create a slice header, and it is created from scratch. It's shown in blue here and is located at memory position 3. The newly created slice header also contains a reference to the backing array, but now is only a weak reference indicated by a dashed arrow, because the garbage collector will not treat it as a live reference. Now, at this point, note that the string and the string header values are never used again. If the garbage collector runs at this point, and remember that it can't just run at any point because it's concurrent, then it will free both the string and the backing array. And now, when we convert the slice header to an actual slice, although the reference becomes a strong reference now, the backing array is already freed. And therefore, the resulting slice is a dangling pointer into invalid memory, and therefore it could be used to perform code injection or information leak exploits. Now, to demonstrate the practical exploitability of vulnerabilities based on unsafe misuses, we created a code injection exploit. It uses an invalid slice like created earlier, and it uses it to change the return address stored on the stack of some function. And then using the return-oriented programming technique, we exploit this to open a shell, which can then further receive instructions from an attacker. There is not enough time in this talk to go over the exploit in detail, but I created a series of blog posts that describe this and actually some other proof of concept exploits. If you're interested in the code and explanations, follow this link shown here. Now let's continue with part 2 about our novel static analysis tool go-geiger. It's used to identify unsafe usages in a project as well as in its dependencies. It's available on GitHub at the link shown here. We designed go-geiger as a tool to identify and count usages of the unsafe API in Go code. There is no analysis of the purpose or danger of these usages done by go-geiger. Its goal is to allow an effective manual auditing of unsafe usages by developers. A key feature is that go-geiger does not only look at a specific piece of code, but it also analyzes all of its dependencies and then transitive dependencies as well. And this is important because those dependencies will get into the resulting binary as well, and they might be hidden or at least not obvious at first to the developer. Now the diagram here shows the design of go-geiger. It first gathers the dependency tree of the code under examination, and then it parses all of the packages contained in this tree to inspect their abstract syntax trees. Usages of unsafe are then identified and classified by match and context type. The match type indicates which part of the unsafe API, that is one of the 4 members of the unsafe package, but also string and slice headers and the uint pointer raw addresses type is used, while the context type describes the syntactic function of the usage. That is whether unsafe is used in an assignment or in a function call or in a declaration of some value. And this is useful to filter the counting to specific types and contexts. Then finally the usages are deduplicated, counted and then shown to the user. And that can look like shown here. These are the results for go-geiger itself. On the right side, the dependency tree is shown with one package on each line. And then on the left, the number of unsafe usages is shown. Packages that use no unsafe are shown in green, while packages that do are red. And then white lines indicate a package that does not use unsafe directly, but one of its dependencies does. To find out how unsafe is used in practice and evaluate go-geiger, we conducted a study using the 500 most starred Go projects on GitHub. We ran go-geiger on them to obtain unsafe usages raw data, and then did both a quantitative study and a qualitative analysis by creating a novel data set of unsafe usages labeled by their purpose. We'll talk about that in a second. Our dataset contains 343 of the projects because the remaining ones did either not compile on our machines or they did not yet use the Go module system, and therefore we were unable to automatically fetch the dependencies and do the analysis. The projects in our dataset are popular. They have between 3 and 73,000 stars with an average of about 8,000. Some of the most known projects in the dataset include Kubernetes, Prometheus or InfluxDB. Including all of the dependencies, there are actually about 62,000 unique Go packages in the dataset, and we found almost 200,000 unique lines of code using unsafe within those. All raw data and scripts needed to reproduce our results have been made available in a public Git repository, so check it out at the link shown here. The goal of the evaluation was to answer 4 research questions. The first question is how prevalent unsafe is in actual Go projects, and the second one is about how deep these usages are located within the dependency trees. The third question is about the distribution of different unsafe keywords, and finally the last question is about the purpose of unsafe usages, which is answered using the novel labeled dataset. So let's look at the first question. There were 9% of the projects without any unsafe usages, 38% of the projects with direct usages, and 91% of the projects use unsafe either directly or through one of their dependencies, well, at least one of their dependencies. Therefore, it can be concluded that unsafe is used commonly. To answer the question about the depth of unsafe in the dependency tree, this heat map shows the number of packages containing at least one unsafe usage on each level of depth in the dependency tree for all projects. Projects are shown on the x-axis while the level of depth is shown on the y-axis. And then the greener a spot is, the more packages are at that depth. On the left is also a bar chart showing the total number of packages summed over all projects on a particular level of depth. We can see that most packages are at depth 2 or 3. In fact, the average is just over 3. So this means that while the packages are not incredibly deep within the dependency tree, they are too far in to allow an effective manual analysis. This is because with each level of depth, the number of packages that we would need to audit increases exponentially. The third research question covers the distribution of different unsafe keywords. Remember, there are 4 members of the unsafe package, and then there's also string and slice header and the uint pointer raw memory address type. We found that uint pointer and unsafe pointer are by far the most important or the most commonly used ones. In fact, they're used orders of magnitude more commonly than the others. Unsafe size of is the next most common, while the others have less than 1,000 usages in our dataset. To answer the last question about the purpose of unsafe usages, we created a novel dataset of labeled unsafe usages. We selected the 10 projects with the most unsafe usages, and then within those and their dependencies, we randomly sampled 1,400 lines of code. And each of these samples was then manually labeled using a custom labeling tool that we developed specifically for this purpose. And the labeling is done in 2 dimensions. The first label indicates what is being done, so be it a cast or a pointer arithmetic. And the second label indicates the purpose or goal of using unsafe in that particular instance. Now this slide illustrates the results for the research question, divided by usages within the Go standard library on the right and application code or non-standard library code on the left. The labeled dataset contains usages of both groups to allow to split the purpose analysis. For application code samples, the most common usage with 58% is efficiency, such as in-place conversions between types. Next, with 28%, serialization operations, such as inferring types during marshalling operations, are the second most common. And then after this, we have accessing C code through the foreign function interface in 6% of the cases, and implementing generics as they are not yet available in 2% of the cases. For the standard library, on the other hand, the purpose of using unsafe are different. The most common is making the garbage collector keep a specific value in memory while a system call runs, and that is using a specific pattern that just uses unsafe. Next, the actual implementations of the type system and memory management and memory layout accounts for 18 and 13% respectively. Interacting with external C code through the foreign function interface is done in about 15% of the cases in the standard library. So let's continue with part 3 about our novel linter tool go-geiger, which can find known dangerous misuses of unsafe. Like go-geiger, it's available on GitHub at the link shown here. go-geiger is built on top of go-vet, which is a standard linter tool that is part of the Go standard toolchain. And then we added 2 new analyses on unsafe. In contrast to go-geiger, go-geiger is actually analyzing the findings and alerts developer of actual problems in the code. Here's a screenshot of go-geiger in action. If it finds some warnings for a package, then it shows the file name and line number to the developer. go-geiger can detect 2 incorrect and dangerous usage patterns. The first one are the conversions between incompatible architecture-dependent types, as we talked about earlier, and the second one are those invalid direct constructions of slice and string headers. We ran go-geiger on the projects we analyzed, and we were able to identify 64 bugs, we submitted 14 new pull requests to GitHub, and then there was also one pull request that we just didn't have to submit because it was already there to fix those 64 bugs. So far, 10 of the pull requests have been merged, and this accounts for 59 or 92% of the bugs actually having been fixed. Finally, let's draw some conclusions. In our paper, we show that the unsafe API can lead to security vulnerabilities in different ways. There can be use after free and buffer overflow bugs, leading to code injection and information leak exploits. Our novel tools go-geiger and go-safer help developers in finding unsafe usages in project dependencies, as well as detecting known dangerous misuses of the unsafe API. It was shown that the unsafe API is actually used commonly in open source Go projects, and we contributed a novel labeled dataset of unsafe usages to examine the reasons why developers use it. Finally, it's important to note that security vulnerabilities can also be introduced without unsafe. Therefore, if go-geiger flags a package as green, that just means that it doesn't use unsafe. It does not mean at all that the package is safe from any security vulnerabilities. This slide contains some of the interesting links shown in the presentation again, which are our tools go-geiger and go-safer, as well as the repository with all our reproduction scripts and raw data. And finally, the blog post series covering some of the proof of concept exploits using unsafe in more detail. These are my sources. A special thanks goes out to Maria Letta for her beautiful Gopher illustrations. Thank you very much for your attention, and now I'll be happy to answer all of your questions.